Hi, we're looking at rational exponents today. This is when you take some base and you raise it to an exponent that is a fraction, right? A rational number. We're trying to understand what that means. Now, to sort of figure that out, I want to tell you a story about a journey you've already taken with multiplication. Okay, so way back when you first learned about multiplication, you learned to multiply two numbers, sort of like this, 6 times 3. And you were given a story about how this meant you were doing a kind of repeated addition, where this was 6 plus 6 plus 6, right? 6 added to itself essentially 3 times, right? That's what we interpreted multiplication as being, a kind of shorthand way of writing repeated addition. And of course that meant that 6 times 2 was equal to 6 plus 6. And 6 times 1, well, you could sort of think of that as just, 1 6 added to itself, just the 1, that's going to be 6. That kind of makes sense. But what happens when we get to 6 times 0? Well, here the story starts to break down because it doesn't really make sense to say 6 plus itself 0 times, right? But you can get a feel for what this must be. You can follow the pattern that we've taken here, where each time this number goes down by 1, our sum goes down by 6, right? We're losing one term of 6. And so if you keep that pattern up, well, it must be that this number here must be a 0. 6 times 0 must be 0. You've gone down by 6. And in fact, if you keep going with that pattern, you can figure out that 6 times negative 1, well, you'd have to go down by another 6. You would get a negative 6, right? And 6 times a negative 2, well, that must be a negative 6 plus 6, right? And you could keep going. You could extend the definition of multiplication, because if you just think about 6 times negative 2 as 6 added to itself negative 2 times, that doesn't make sense, right? But by extending this definition logically, we can make sense of that operation. So what we did is we started with multiplication of natural numbers, and then we extended this to multiplication of integers, positive and negative, including 0. And then you did this even further. You learned how to do 6 times, let's say, 1/2, right? Multiplication with rational numbers. And we saw that this was, 3. And so you were able to take this definition, expand it from natural numbers to integers to rational numbers. And that's what we're trying to do today with exponents. And we've already sort of gone most of the way down this journey. We started out, we saw that 6 to the power of 3, well, that would equal 6 times 6 times 6, right? 6 squared, that's 6 times 6. 6 to the first power is just 6. And then we saw that 6 to the 0 power, well, yes, 6 multiplied by itself 0 times doesn't really make sense, but following the rules and laws of exponentiation, we saw this must equal 1. And then 6 to the negative 1, well, we saw that this sort of produced a reciprocal effect. This was 1 over 6 to the first power. 6 to the negative 2 power, that was 1 over 6 squared. And so we were able to develop these ideas, and we want to extend this now to have a rational number here, a fraction in the exponent place. Okay, so that's the idea. That's the story I want to tell you just to justify sort of what we're doing here. And I'm just going to tuck this into a corner. How about right over here to store that? Okay, so let's talk about rational exponents now. What if I have a number like 4 to the 1/2 power? Okay, it's a fraction up there, a rational number in the exponent, and I want to know what this equals. I'm just going to call that x because, I don't know what that is right now. We can sort of take a guess, right? So one way we could do this is think about, well, 4 to the 0 equals 1, and 4 squared equals 16. So 4 to the 1/2 power, that's, halfway in between 0 and oh, actually, I shouldn't do that. I should say 4 to the first power. Okay, 4 to the first power, that's just going to be 4. So 4 to the 1/2 power is sort of halfway between 4 to the 0 and 4 to the 1. So we might estimate this is maybe 2 or maybe 2 to 3, something like that, right? We can estimate what this must be. But how do we actually calculate? How do we actually find what this is going to be? So to do this, I want to think about the exponent rules and laws that we've already looked at. Okay, so we've looked at a few and they're going to help us. The first one we looked at was some a to the m times a to the n would equal a to the m plus n, right? You add those exponents together. And the other important rule here we could look at is that some a to the m power raised to the nth power again would equal a to the m times n. Okay, so these are two rules about how exponents work, and let's see if we can adapt them to work with a fractional or rational exponent like this 1/2, right? So let's say I've got my now 4 to the 1/2 power multiplied by 4 to the 1/2 power. This should give me 4 to the 1/2 plus 1/2 power, right? And that's just equal to 4 to the first power, just like that. So that's just, of course, 4, right? So what I'm saying here is x to the 1/2. Well, let me call that x, okay? 4 to the 1/2, let's call that x times x equals 4. I'm saying this is x squared equals 4. If I'm trying to solve for what x is, well, x must equal the square root of 4. And that means 4 to the 1/2 equals the square root of 4, okay? So that's actually what this is. And that, of course, is equal to 2. And so our guess here that it would be somewhere between 2 and 3 was actually a really good guess. It turns out 4 to the 1/2 power is going to be 2. Okay, that's what it's going to be. And now let's check it again with this other rational, this other exponent rule for adapting it with rational numbers here, okay? So let's try here, again, 4 to the 1/2. And what I'm going to do is I'm going to square it. So if I square this, I should get 4 to the 1/2 times 2, which is just going to be 4 to the 2 over 2, which is just 4 to the 1, right? So this is just 4. And 4 to the 1/2 power, again, we said that was x. Let me call this, so it's going to be x squared equals 4. X equals the square root of 4. Once again, 4 to the 1/2 power equals the square root of 4, which equals 2. Okay, so it works with both of these rules. We've sort of figured out what it means to take a number and raise it to the 1/2 power. What it really means is you're taking the square root of that number. All right, so let me sort of get the rule here. It's essentially we're taking the square root of that number. That's what the raising something to the 1/2 power actually means. Let's see if we can generalize this now. Now, instead of taking a number and raising it to the 1/2, I want to use any number here in the denominator, a to the power of 1 over n. What does that mean? What is that going to equal? So let's start with an example. Let's try 8 to the 1/3 power. What does that equal? I'll call that x, okay? And again, I'm going to use those exponent rules and sort of extend them to fractional exponents like this. So what if we have 8 to the 1/3 power, but then cube it, right? I'm saying what this must equal is then a to the 3 over 3 power, which is just a to the 8 to the first power, just 8, right? And so essentially I can say this 8 to the 1/3 is x is equal to x cubed is going to be equal to 8. And so now I can solve for x. So x must equal the cubed root of 8. So we're saying that 8 to the 1/3 power equals the cubed root of 8, just like that. And of course, that would equal 2. But the idea is you can sort of see this pattern where this denominator is becoming the index of this radical, right? It's becoming like that root. So we can generalize this now. Let's just talk about some a to the 1 over n power, right? So in this case, we can say we've got some a to the 1 over n power. And if I take this and then raise it to the n power, well, then I'm just going to get a to the n over n. And that's just a, the a to the first power, just a, right? So I can then essentially take this a to the 1 over n power, raised to the n power equals a, and then if I sort of take the nth root of both sides, well, these ends will cancel, and I'll just be left with a to the 1 over n equals the nth root of a. And that is actually the general rule here for what this means. What we're saying is that any kind of base raised to the 1 over n power is the same as taking the nth root of that base, okay? And so we can see that this denominator becomes the index of a radical. That's what this is equal to. Let's see if we can generalize this even further. We're looking at the fully generalized rule now. We're trying to figure out if you raise a number to any arbitrary rational number, any arbitrary fraction where the numerator can be anything and the denominator can be anything. Let's look at an example to illustrate this. How about 16 to the 3/2 power, okay? Essentially what I can do is I can take that exponent, that 3/2, I'm going to split it into 16. Let's say 1/2 times 3, okay? That's going to be the same as 16 to the 1/2 power, all raised to the 3rd power, okay? Now I know what 16 to the 1/2 power is going to equal. That's going to equal the square root of 16. But I still need to cube it all, okay? Now the square root of 16, that's just going to be 4. So I'm left with 4 cubed, and that should equal, well, 4 times 4 is 16. 16 times 4 is going to be 64, okay? So there we go. We were actually able to use the rules of exponents to evaluate this kind of fractional exponent. Okay, let's try and derive our general rule here now. So if I have, in general, any a to the m over n, I can treat that as a to the m times 1 over n, which is the same as a to the m raised to the 1 over n power. And so that's going to give me the nth root of a to the m, right? That's exactly what this does. Now I could also look at this a different way. I could see this m times 1 over n, well, I could reverse that because multiplication is commutative, and so I say this should be the same as a to the 1 over n times m. And now I'm sort of doing this 1 over n first, raising that to the mth power, and so essentially I'm taking the nth root of a first and then raising that to the mth power. So that should be this exact same thing as what I have over here. So there's two ways we can sort of evaluate these kinds of expressions. It turns out we'll often be doing it this way first, because if you take the nth root of a, you shrink a, it gets smaller, and then later you can take that smaller number and raise it to a higher power. If you do it first here, you're taking a number and then making it really big and then trying to take the nth root. Sometimes that's just a little more difficult, but, you know, mathematically should be equivalent. All right, so in general, here's what the rule looks like here for rational exponents. It's exactly what we just found. Any a to the m over n power, you can think of that as either the nth root of a to the m, or you can think of it as the nth root of a raised to the mth power. Both going to be the same. Now, notice there are some caveats here, okay? So the first thing we want to look at is m and n are going to be integers, right? Because that's the definition of a rational number. It's a ratio of integers. That's okay. We're also saying this is going to be for when this fraction is in lowest terms, okay? So not some multiple of something. We're also saying that this n is going to be positive. If we have a negative exponent, we know what that means. We're going to take like the reciprocal, so we can work with that. But this extra caveat here is saying that if n is even, then we require this base essentially to be not negative, okay, greater than or equal to 0. And the reason why is because you can't take the even root of a negative number, right? You can't take the square root of -1. That will give you an error. You can't take the 4th root of -1. That will give you an error. So whenever n is even here, whatever's inside here cannot be negative. That's the only extra thing. Okay, so there you go. That's what it means to have a rational exponent. Essentially, if you take a number, raise it to some fractional exponent, the denominator becomes the index of the radical. It's the root, and the numerator just becomes the normal exponent, the normal power you would raise it to. And it's actually not too hard to work with. Now, there are some caveats that we mentioned, and the next video is going to dig a little deeper and sort of show you some warnings about why we need to keep those caveats in mind. I'll see you there.